Hello friends, welcome to engineering tutorial. So we'll continue our discussion related to sensors and transducers. In the previous video, we discussed about the magnetostrictive transducer for measurement of force and pressure. In this video, we will extend that discussion again on magnetostrictive transducers, but in this case, the parameter under measurement is acceleration. So we'll be using the same transducer with some modifications to measure acceleration. So it is magnetostrictive accelerometer, which is the topic of discussion. So again, as I said, the operating principle is the same in both the cases, which is the magnetostrictive effect. So the property is that when the ferromagnetic materials, which are rich in the dipoles, the domains, when it is exposed to a fluctuating, changing magnetic field, it undergoes change in its shape and size, dimensions. And when the reverse happens, that is, when the same ferromagnetic material is exposed to stress, mechanical force or pressure, it undergoes changes in its magnetic characteristics, especially the parameter, the characteristic which we are interested in is permeability, relative permeability. Relative permeability changes with respect to application of force or pressure or stress. Okay. So this parameter we are going to use to measure these three, and from these we will measure the acceleration. Okay, so how we can do that? We know that the the main design characteristics which is used here, the ferromagnetic material, it is used in the form of a solenoid or a toroid. Okay, a ferromagnetic material with number of turns of wire closely wound, and from that we try to measure these things. So we know that the magnetic flux density due to a solenoid or toroid, it is given by this: B is equal to mu 0 mu r n I, where mu 0 is the absolute permeability, which is constant. Okay, this is constant. N is the number of turns of wire, that is also constant, and the current is kept constant, the current which is passed through the solenoid or toroid, that is also kept fixed. So the only thing which is variable is this relative permeability, and this changes with respect to the applied force, pressure, stress. Okay, this. So as the magnetic flux density changes, the magnetic flux also changes as per this. Phi b is Ba cos theta. It is the dot product of the magnetic flux density and the area element vector. We all know about magnetic flux, we have discussed in the previous video. And then as per Faraday law of electromagnetic induction, an EMF is generated with respect to the fluctuating or changing magnetic flux, which is given by this N d phi b by dt. So here, change in relative permeability because of the applied force, pressure or stress contributes to a change in magnetic flux density. Change in magnetic flux density causes a change in magnetic flux, and then change in magnetic flux contributes to a generation of EMF, which is a voltage signal, and then with the help of suitable signal conditioning techniques we can convert it into current, and suitable amplification, linearization procedures are used, but that is a different thing. But we are getting a measurable electrical signal. So the main essence of any sensor or transducer is to convert a mechanical or physical signal, okay, to electrical signal, because we can measure electrical signal in terms of voltage or current. So electrical signal means voltage or current. So this is happening here. So we have to identify a parameter which responds to that external mechanical signal. So here the parameter, the electrical or electromagnetic parameter which is responding to the physical signal. This is the physical signal, force, pressure, stress, this is the physical signal. The parameter which is responding to this is relative permeability. Relative permeability causes a change in flux density. Flux density causes a change in flux. Change in flux produces a EMF. So this is the basic principle. So we all know that. Now the design, the construction is the same. We have a ferromagnetic coil which can be in the form of a solenoid or a toroid. Then we have a protective case, then we have wires for the measurement of the EMF. Now the main design principle which is used here is that this thing which channelizes the whole impact, the mechanical parameter, the force, the stress, the pressure, whatever, when it is subjected to acceleration, when it is subjected to acceleration, that force is channelized here at this point, the impact point. And this thing which lies above the solenoid or toroid, that is of fixed mass. It is of fixed mass, whether it is in terms of grams or kg, whatever it is, this mass is fixed. So when the mass is fixed, we know force is equal to mass into acceleration. Okay, so when this mass is fixed, then force is directly proportional to acceleration. So the force that we measure, it is directly related to acceleration, and mass is the proportionality constant in that case. So we can get A is equal to F by M. So the same principle is utilized here. Okay, so here the stress or the force, whatever it is which we used for force or pressure measurement, same, stress is equal to force per unit area, or pressure is equal to force per unit area. Force is equal to mass into acceleration by area. So as mass is fixed, area is fixed, the surface area is fixed, it is constant, then we can get acceleration as this: stress area divide product of stress area divided by mass. Or we can also get it in terms of force as A is equal to, as I said here, F by M. In this way also, if we are using a force sensor, magnetostrictive force sensor to measure acceleration, we can use this relationship. And if we are using a pressure sensor or transducer to measure acceleration, then we can use this relationship. The important thing is that mass is fixed, area is fixed. Okay, so the calibration has to be done in terms of acceleration or stress in case of pressure, magnetostrictive pressure sensor, which is used as an acceleration sensor, or the calibration has to be done in terms of acceleration and force when it is the force transducer which is used for acceleration measurement. See, a sensor is the basic working principle is the same. So it is up to the user, the one who designs the sensor or transducer, to decide in what way he or she wants to use it. Okay, it's up to the manufacturer. So the operating principle is the same. Here we can use any appropriate relationship to calibrate it to give us a certain output. So when it is calibrated to measure force, the output will be given in terms of newtons. When it is calibrated in terms of pressure to give us the output in terms of pressure, Newton per meter square or Pascal, whatever it is, bar. Then when it is calibrated to measure acceleration, the output will be given in terms of meter per second squared. So it's up to the manufacturer to decide in which way he or she wants to calibrate it, but the operating principle is the same. So here always remember, when acceleration is in terms of the stress or pressure, this is the relationship, and when it is in terms of force, it is force by mass, and both the cases mass is fixed. Mass is fixed. In case of pressure, the area is fixed. Mass is fixed, area is fixed, constant. Okay, so here acceleration is directly proportional to the stress applied. In this case, acceleration is directly proportional to the force applied. Okay, so this is the thing. And there is also a relationship which is directly related to the applied stress and the EMF, which is this, which we have also discussed previously, where the EMF, the time varying EMF, is equal to SAN d sigma t by dt, where sigma is the stress applied, S is the sensitivity of the sensor. So sensitivity is output by input ratio, change in output divided by change in input. So here the output is in terms of EMF, that is voltage, and the input is in terms of stress, that is Newton per meter square, or whatever other units of pressure which is used. Then A is the coil area and N is the number of turns of wire. Okay, so this is the relationship which is related in terms of EMF, that is voltage, and change in stress with respect to time. Okay, so let us try to understand this thing from a 3D perspective. So here we have the magnetostrictive force sensor, call it, or pressure sensor, or accelerometer. So here this whole setup, when it is connected, it is subjected to acceleration, whether upwards or downwards. So in this case it will be upwards or downwards, because we want this force or pressure, the impact, to happen at this point. Okay, we want the impact to happen at this point. So this up and down movement is channelized into the force or pressure, which concentrates at this fixed mass. Okay, at this fixed mass. So the force, mass into acceleration, is subjected to this solenoid, and as a result of this force there is a change in relative permeability, and this change in relative permeability causes a change in the magnetic flux density, and then this change in magnetic flux density causes a change in magnetic flux, and that causes a change in EMF as per Faraday's law of electromagnetic induction. So if this is acceleration, that is upward or downward. Now if we want sideways thing, so if we have a requirement where the acceleration is along the horizontal direction, in that case the orientation, the location will be something either like this or this, depending upon the direction. So in that case it will be like this, left and right movement. Again the force will be channelized here, and it will be converted into change in permeability, permeability to flux density to flux, and then EMF. Okay, so either this kind of movement in case of horizontal acceleration, and in case of vertical acceleration this is up and down movement like this. Okay, so this is the basic principle. So this is the basic design principle of the magnetostrictive accelerometer. Okay,